Welcome to the talk on asynchronous database access with Gino. I am Fantix Wang Chuan, currently working for the University of Chicago as an architect at the Center for Translational Data Science. I've been working as a Python developer in Beijing for 12 years in about 10 different startups. I'm a big fan of open source. I've started many toy projects on GitHub, but most of them are forgotten. Gino is probably the only active project remains. I've also contributed to AsyncPG, UVlib, and CPython with awesome Magic Stack folks. I've been using PostgreSQL for most of the time, so I'll use it as an example in this talk. To access PostgreSQL in Python, my choice was usually CyclePG2. It's a DB API implementation written in C on top of libpq. It's super reliable and widely adopted. It's usually fun to deal with DB API and raw SQL. But when we started to repeat writing the same code again and again in large applications, it turns into a distraction. As many people usually say, the developers are more expensive than the machines. So in this talk, we assume development performance is an important factor in our equation. There are many ways to improve it. For example, HDB is an exciting solution to leverage PostgreSQL to manage data and build applications. It provides lots of modern features and innovative methodologies, and development performance is just one of its advantages. There was a great talk in PeterPy 2018 on HDB, video link here. There are also other tools and techniques to improve development performance between using advanced solutions like HDB and using raw SQL directly. ORM, or Object Relational Mapping, is one of such techniques. SQL Alchemy has been my favorite. It has two parts. SQL Alchemy Core for building SQL and processing results, and SQL Alchemy ORM for object mapping and session management. Then we had the asynchronous frameworks like Twisted, Tornado, Gevent, or Async.io. They are extremely useful in leveraging CPU and memory resources to support large scale of IO-bound concurrency. For example, instant messaging servers or chatbots, game servers, and some API servers with WebSocket support. The asynchronous framework could cooperatively work on lots of lightweight tasks at the same time. It tries to utilize all the free CPU time waiting for I/O as much as possible. For example, all 4 clients here are waiting to receive messages from different users, but that doesn't stop the application from forwarding hello to user 2, 3, and 4 in the first broadcast. The world came to client 2 when the first broadcast of hello was still in process. And client 2 started to handle the world as soon as the first broadcast is finished. In such applications, database access is usually required. How to properly blend database access into asynchronous programming while keeping a reasonable development performance and experience. This is our primary topic today. 5 years ago, the author of SQL Alchemy wrote a great blog post linked here. He raised a good point that because modern databases are extremely fast and they're usually placed in a super reliable internal network, the Python operations to access the database should not be considered as IO-bound comparing to a slow typer in the chat room or the Python interpreter itself. In other words, the database access is so fast that there's very little CPU time to recycle by asynchronizing such operations. Given the second point that this is also taking time to manage events and schedule asynchronous tasks, I think it's a very bad idea to choose asynchronous programming only because it sounds faster. Believe me, it only makes things slower and more complicated. However, in scenarios where asynchronous programming is truly needed, does that mean that we could just use the blocking database access method as it is? Let's take a look at this piece of code. So it simply implements an API that returns a timestamp from the database while simulating some asynchronous work in the middle. We're following the best practice to align the ORM session scope with the requests, so everything should just work. Unfortunately, our server will freeze forever shortly after the number of the concurrent users bumps up to 11. This is because the default maximum size of the database connection pool is 10. In this case, when 10 requests are waiting on the asynchronous work here, the 11th request came in and tries to acquire a new connection from the pool that is already exhausted. Therefore, task 11 will block not only in its own task, but also blocking the whole main thread, because it's not an asynchronous operation. That means none of the first 10 tasks would ever get a chance to run again and release any connection back to the pool, thus leading to a application level deadlock. There are many ways to avoid such resource starvation. For example, we could always manually return the connection back to the pool before any awaits, but this can be easily forgotten and error-prone. So the golden rule is never, ever block the main thread, because any operation that may block will eventually block. This is the Murphy's Law, asynchronous addition. So one would say, let's put the database code into threads. I gotta admit that this is frequently recommended and it usually works. But how do we define database code? Does this count? Because traditional ORMs sacrificed so much explicitness for convenience, we don't know for sure if this statement would trigger a select in the database or not. Personally, I never tried to put database code into threads, so I'm not the best person to speak of it. But the idea really scared me, to think about thread safety all the time. I would rather just use Celery to deal with all the asynchronous operations once for all and keep the application server clean for just synchronous frameworks like Flask and SQL Alchemy. Alternatively, we can embrace a purely native asynchronous ORM. I mean, why not give it a try? But there has to be one. Back in 2017, when I was facing this choice for a new product, there wasn't a lot of options for me. Before Async.io, there was TX Postgres for Twisted, CycleGreen for gEvent and Eventlet, and a bunch of other CyclePG2 based solutions. They worked fine for years. Until the super challenger combo of performance monsters came into our sight. Powered by the force of Cython, UVloop, and AsyncPG made PostgreSQL access insanely fast in Python. The asynchronous overhead we mentioned before still exists, but the performance boost fully covered the loss. AsyncPG is for executing raw SQLs. Then we needed some sugars on top of it. These were my options back then. They all solve some part of the problem, and I believe they're very useful for their users, but they're just not good enough for me. Then I decided to write my own asynchronous ORM. I really appreciated these 3 projects for the inspiration. Following GNU's recursive definition style, I named this project Geno, as Geno is not ORM. So why not ORM? At first, it was just me not wanting to build a fully featured ORM, but later I found the idea rather appealing, so I turned to use it to scope the software. In traditional ORMs like SQLAlchemy, objects are stateful, managed by sessions. This is handy and powerful in regular synchronous applications, but this means huge implicitness that may cause endless troubles in an asynchronous context. And that is also the reason why it is so hard to port traditional ORMs into async I/O. Instead, Geno model instances are purpose or plain old Python objects. They're just regular Python classes and instances in the memory. You can create as it is, access as it is, or even copy as it is. No magical database access involved. Zero surprise. For example, here's a simple user model. The only magical word here is __ table name, defining the name of the table in the database. This is also Geno following SQLAlchemy's flavor, trying to keep a familiar taste. But Geno has nothing to do with SQLAlchemy ORM. I mean the ORM part of SQLAlchemy. Do you still remember the 2 parts of SQLAlchemy I mentioned earlier? Geno is only heavily depending on SQLAlchemy core. The db.column, db.integer, and db.string are vanilla SQLAlchemy core types. db is just providing a scope for shortcuts. So behind the scene, it is almost equivalent to directly use SQLAlchemy core like this. The DB instance is just a SQLAlchemy metadata instance holding all the defined table instances below. The automatically created SQLAlchemy table instance is stored and referenced as user.__table. Back to our example, with the user model, we can then create a new user instance, access its attributes, or notify them. Everything just works purely in memory, no implicit database access. There is no limit at all for such classes and objects, but the __ table instance is not yet involved. The __ table instance can be used to construct SQL with SQLAlchemy core like this. And here's the SQL. Then let's try to simplify the query into this. It produces identical results, but it's much shorter and more intuitive. As the query instance is just a normal SQLAlchemy core query, we could just execute it with a normal SQLAlchemy engine, but as we described previously, this is not the preferred way in my asynchronous application. It's shown here just because we can do so. Being able to define tables and build queries is not enough. We need to use async PG to execute our queries. In Geno, we're following the SQLAlchemy way. It's not just running SQL and return results. As demonstrated in this diagram, the dialect in the middle here is the boss behind the scene, managing all the compilers, bind processors, result processors, describing the SQL, and assembling the results. It's actually the key to properly implement such async PG dialect for SQL Alchemy in order to be more compatible with SQL Alchemy and leverage its functionalities. All of this is encapsulated and well polished in Gino. To execute a SQL Alchemy query, we just need to import Gino. Then we need an asynchronous engine first. The await here is important. It waits for the async PG dialect to establish the initial database connection for the pool using async PG. Then we execute the query with Scala here. It executes the query and returns the Scala value of the first column in the first row, if any. Underneath, this is also done through async PG. Okay. So now we're able to define tables in Gino as models, build queries with models, create Popo instances that is not used yet, and we're able to execute any SQL Alchemy core queries asynchronously in Gino. And such queries don't have to be defined in Gino because essentially they're all SQL Alchemy core queries. So next, let's try to make the Popo instances useful by loading the query results into the Popo instances. Continue with our previous example. This is our query. This is our engine, and they're all the same. Now let's execute the query with the loader. So the loader execution option is recognized by Gino engine and used to map the query results into objects. In this case, the loader is user, meaning every row in the query results will be loaded into a user instance. As we're using engine.first here, only the first row is returned and loaded if the query result is not empty. Therefore, we get a user instance. It's just a plain Python object. We could access its attributes freely. With all these, we could already do a lot of things with async PG and SQL Alchemy. But why not just make things easier when we can? For example, the same query can be done in a short form like this. This is a more intuitive way to construct the query, assign a loader, execute, and fetch the result. The Gino connector here is an extension added to all SQL Alchemy core queries after Gino is imported. It is used to expose the Gino APIs in a more convenient way inline. So the only missing part here is the engine. In order to make this work, we need to bind our engine to the context where all models have access to. That is our global DB instance. Because all the models are defined as subclasses of db.model, they can find the engine through db.bind. The db attribute here is actually the same one as SQL Alchemy metadata.bind. Okay, while SQL Alchemy allows this, to create an engine and set it as metadata.bind, and at the same time, Gino doesn't accept it because we need the await keyword to initialize the async PG connection pool, and there is no place for await in an assignment statement. So instead, we use await db.setBind. It does exactly the same thing, but in the asynchronous way. There's also a common practice to clear and close the bind engine like this. It's pretty straightforward as the code explains itself. Nowadays, SQL Alchemy no longer recommends the use of bind, and it will eventually remove it in the next major version of SQL Alchemy. But it's such a convenient feature for Geno to deal with model-based CRUD operations, aka CRUD, so that I kept the bind in Geno 1.0. For CRUD, here is the create. Very straightforward. Behind the scene, it uses the returning statement to fetch the database-generated ID field and load the row back to the instance Alice. Retrieve is simple too. We tried something similar before. User.query is just select everything from users and load the rows into user instances. So we got the same row in two different Python instances. They have identical values, but occupying different memory spaces. Update is separated into two steps. The chainable update method collects all the changes, also updating the memory values. And the enclosing apply executes the update SQL. So it needs to be prefixed by await. Yeah, the memory values are different now. If we don't apply before, the memory values will still be different, but the actual rows in the database won't be touched. At last, delete the row by its primary key. There are many other convenient sugars in Geno. I'll leave that surprise for you to find out. One frequently asked question is how Geno handles relationships. The short answer is it doesn't. At the beginning, it was because I don't know how to design a proper relationship system in an asynchronous ORM that wants to be both explicit and convenient. It's really hard to balance as relationship is the #1 jar of implicitness bugs and gotchas. But after the loader system was added to Geno, I found it so powerful and flexible that I don't even need a relationship system in Geno anymore. With some reasonable extra coding, developers could compose super complex but efficient queries explicitly, even with multiple CTEs, and load the whole result into connected objects with a predefined loader. It's pretty intuitive to write complex loaders once you get the idea. Let's try a more complex query with two models. We are adding a new column to our previous user model. It's a foreign key referencing the team the user belongs to. The foreign key constraint here is not a must. It works just fine as a normal integer column. Geno is not assuming anything here because it doesn't support relationships. I think this is now an advantage for flexibility. Okay, we use this foreign key here anyways to make it more obvious. Team is just another model, nothing fancy. Let's create a team delta, create a Bob for team delta, then we write the query to load this many-to-one relationship. User.join team is another Geno sugar to represent the tables with models. The query gives us this result. So user.load means we are still returning user instances per row, but team equals team means Gino will load those values of the columns that belongs to the teams table into a team instance and set it to the team attribute of the user instance on the same row. The lowercase team here is just a random name. It can be anything, and there's no limits on the user class at all. You can define setter properties or whatever makes sense. And yeah, we can verify that who.team.name is just team delta. Okay, I'll stop here. I think that's enough details to show you how my ideas about asynchronous ORM and why Gino is not a traditional ORM. The idea is really to be explicit, even that means to sacrifice some convenience. Also, building on top of SQL Alchemy Core gives me a lot of leverage. For example, using Alembic to manage schema migrations is simply supported out of the box. And if people are already familiar with SQL Alchemy Core, they could start coding with Gino very easily. It feels familiar, and there are already a lot of SQL Alchemy Core questions answered on Stack Overflow, so it'll be less likely to get blocked in building queries with Gino. There are many more we didn't cover. The Gino documentation is a good place for the next steps. And me and Tony, he's a great developer and contributed a lot to Gino. We're actively working on the roadmap to bring in more features and fixes. After Gino is created in 2017, there were more awesome asynchronous ORMs coming up. They have slightly different tastes than Gino, but also providing many exciting features. At last, HDB has just released the fourth alpha version of its 1.0 as I was making these slides. Together with Gino, these are my two favorite ways to access the database in asynchronous applications. Please feel free to give it a try if you are interested. It's now delivered with an interactive online tutorial. Thank you for watching.